So we have the t plus 3 over t times t squared plus 1, which we'll write as a over t and then bt plus c over t squared plus 1. So once again, then, the a would be the residue. If you thought of multiplying through by the t, your residue would be t plus 3 over t squared plus 1 at your pole 0, which would be 0, and so the a would be 3. And then for the quadratic factor of the original denominator, you would work on the b and the c together with complex numbers if you do poles and residues. So your residue would be the t plus 3 over t, and your pole 0 is I, the same as it was for the other problem I did. So bt plus c at I would be the value of the residue t plus 3 over t at I. So that would be 3 plus I over I. And again, to match this complex number to this one, you have to get standard form. You have to get the real denominator. So the trick is always that you multiply by the conjugate of your denominator. That gets you a positive denominator. So by minus I, because I square is minus 1 and minus I square will be 1. So your c plus bi will be this numerator times minus I, which will be minus I square and minus 3i. So this is 1 minus 3i. So c plus bi is 1 minus 3i. So c is 1 and b is minus 3. So that means then that this part of the problem with the limits 1 to root 3 would be the a, which is 3, dt over t from 1 to root 3. Okay, that's going to be logarithm. And then what you're going to have is minus 3, the bt plus c over t squared plus 1. And so this will split then into two integrals. Okay, so here with this one, you can see that's logarithm. So it's 3 log 1 to root 3. And then what I have done is I've split this one into two parts. I'm looking at the minus 3t over t squared plus 1. I factored the minus 3 out, and I divided and multiplied by a 2 so that I'd finally have a 2t over t squared plus 1. That's kind of the same trick that I did here with this one, where I factored out the 1/2, and then I put in a 2 there and divided by a 2, so I'd have 2x over x squared plus 1. I've done that here, so I'll have a 2t over t squared plus 1, so that this is natural log of the denominator. If that's u, this is du. But rather than doing it with a formal change of the letter to u and the limits, I just saw that this form will give me the logarithm and stayed with the original limits and the original variable. And then here I have the dt over t squared plus 1, and that's arctangent. So then it's a question of putting in these limits, which is messy, but I think this is what you'll get. And remember that we did part of the problem separately, so that's why the blue pen goes here, finally up here. So we have the log 2 root 3 from the first part, and then we have the then this part. You see, you have log 4 minus the log 2, and so that's over here, log of 4 over 2, and the minus 3 halves. And then we have the 3 log root 3 from this first integral, which is there. So this integral is there, and is finally here. And then this one is this part, and that's finally here. And then the arctangents give you pi over 3 minus pi over 4, which is pi over 12. And so if you mess with the logarithms enough, you can get these steps and finally get to what the book has. This is all kind of messy, but it'll go. And so notice if you look at the maple, that are on the back, where I say some denominators have irreducible quadratic factors. We have the convert par frac. Maple hasn't done the problem the way that I did, and it may be that it's better not to have, but anyway, in partial fractions you have number 9. Then if you want to integrate the original one, you see answer 10, and if you take the 2 logs that are in Maple's answer, you can match that up with this. You see, because your 2 log 3 is log 3 square, which is log 9, and your 1/2 log 2 is log square root 2, and so you have log 9 minus log square root 2, and the difference of the logs is the log of the quotient. So you can reconcile what the book has with formula 10 in the maple, all right. Okay, so the last one. Notice that some of these problems are improper fractions. And if you do with the calculator or maple, that doesn't matter. If you notice with the maples convert par frac, it just goes ahead and gives you the x squared plus 1 that you get if you divide this down using long division, and then it gives you partial fractions for the rest of it. So if you're doing this by hand with your improper fraction, first divide it down with long division. So what goes here times what's here brought over here has to be identical to the line above it. And then whatever this is multiplies all the other terms, and you go across. Then you subtract, so you change sign, and you see the degree here is still as much as this is, so you have another term, so the 1 times x squared and the 1 times minus 1, and you subtract. So your original fraction is the quotient, x squared plus 1, and then the remaining fraction is 1 over x squared minus 1. So then you do this in partial fractions. It's very much like problem 1. And you can do 2 equations and 2 unknowns. If you really don't like my poles and residues, I don't care. But A would be the residue here, which would be 1 over x plus 1. And then at the pole, that will give you a half. And the B would be the residue at its pole, which will give you minus a half. And you notice then that if you do the partial fractions and check the addition, it works out to give you the 1 over x squared, you see, because the x's cancel and you have 2 over 2, so 1 over x squared minus 1. So however you get them, these are the partial fractions. So the original problem then is your integral of this part and then half integral dx over x minus 1 for the first partial fraction, minus a half dx over x plus 1 for the second partial fraction. And these integrate pretty directly. Here, these are both logarithms, and you could combine these. You have difference, so it's quotient. And then if you want, you can take the half power, and so you can write it like that. So you could write your answer any of these ways. And let's see. If you look at Maple's answer, the 12, it has this, I guess. Well, what we will do next week then, we will talk about how you do definite integrals when you can't get an antiderivative as a function that you know. A function that you know, like the trig functions or sinh and cosh, for example, are what you call tabulated functions, or what you call elementary functions, in that somebody at some time found the appropriate power series and made tables of values which now you could get out of your calculator or computer. So those are what you call closed form solutions. Well, there are a lot of definite integrals where you cannot get a closed form solution, but there still is an area, or whatever the integral represents. So then we have numerical methods, and that's what we'll talk about on Thursday. Simpson's rule and the trapezoidal rule particularly. And then we will talk about what are called improper integrals, where you're working with definite integrals but they go to infinity, or they include a vertical asymptote at an endpoint, something like that. We'll do that sort of thing on Friday. So work on the test and have a good week. Happy